let's take a look at another graph problem, round trip. So what's going on here? We have a graph with n vertices and m edges, and we want to find a path in the graph, basically a cycle, right, that goes through multiple cities and returns to the starting city. So what does this mean? It just means that you can't go like back and forth along one road, right? That's boring. You should go to at least 2 roads, and also no repeat cities, right? So here's the input, the example input. And so like 1, 5, 3, 1 is a perfectly reasonable round trip. 1, 5, 1 is not, right? Because you can't go back and forth along the same road. That's too boring. You also can't like reuse vertex twice or something. But yeah, so basically there's like 3 answers here, right? There's this one, and then there's this one. And you just need to give any of them. And if there's no cycle in the graph, then you say impossible, right? This is basically just describing a cycle. And the graph has 100,000 edges. So yeah, this is the sample input. Their answer is 3513, 3513. Sure. I mean, that's the same as like 1351, right? Notice that they have the first and last vertex here twice. So this is a perfect problem for a DFS, a depth first search. We've mostly been doing BFSs, breadth first searches so far. So the difference between a breadth first search and a depth first search is that in the depth first search, the breadth first search was sort of slowly expanding out, sort of layer by layer. Right, you would do like 1, 2, 3, right, 1, and then the children of 1, which are 2 and 3, and then the children of 2 and 3, which are 4 and 5. In a depth first search, you just like follow something until it's over. So if you did a depth first search on the graph, you would go 1, and then maybe you would go to 2, and then maybe you would go to 4, and then 5, and then 3, and then you would see that we're back to 1. Right, of course you don't repeat. And the really nice thing about a depth first search for this problem is there's this nice property that when you've seen an edge already, it's always an upward edge. It's always to one of your ancestors. Right, so like it's not possible that we could have an edge out to, I don't know, like here, to some child of 2, for example. And the reason is just that to get to the 4, right, from this child, we must have already explored everything, down here. And if we'd explored everything down here, then we would have gotten to the 3 from here. So there can't be any edges up like that. The only edge that you can have from the 3 is either to new stuff, or it's to one of 3's direct ancestors. That's what this diagram is trying to explain as well. And so that's really nice, because if you have an edge from 3 to one of its ancestors, then that's a cycle. Right? Like if there was a 3 to the 4, then the cycle is like go up from 3 to that ancestor. In this case, we have an edge not from 3 to 4, but from 3 to 1. And so you can get a cycle, right? Sort of one half of the cycle. This is 3 to 1 edge, and the other half of the cycle is this path of ancestors, up from 3. And they both, meet at 1 and start at 3. So that's the cycle. So that's the problem, basically. It's just to do this BFS. So let's do it. And we are going to do it in Python. So let's read N and M. And we'll put the edges. There would come 1 index, but we prefer the 0 index one. We'll probably declare our edges. Okay, and now we just need to do DFS. So I said we needed to follow sort of the ancestors back, so we're going to keep track of the parent of everyone. And so now we need to DFS, and we can't just DFS like one node, by the way, because there might be disconnected pieces, so you might have like 6, 7 over here. So we're just going to DFS and everything. And that's not quite right, but I'll fix it up later. So the idea is that to get into DFS, we should have already set parent. So let me do that. Okay, and then for all of my children. Okay, so if it's the parent, we don't want to do anything, right? If it's not the parent, and we've already seen it, in this case, as some parent, then we find this way. Okay, so we'll want to eventually print out the answer there, but I'm going to do that later. And if we haven't seen it before, then it's a new child. So we are its parents, and we can DFS to that child. Okay. So here we only want to go in if we haven't seen that guy before. So let's do that. And this might be it, actually. Yeah, I should probably copy the sample. Lift. There's no other condition there, just else. Right, this is the right way of saying you already have a parent. I think it's still like C++, so I use Sentinel. Okay, so this is saying that we found a cycle between 5 and 1, which seems false. That's good. And now let's actually generate that. Okay, so we set the cycle. Well, one path of it was this back edge, and the other path was up through here. So, in fact, the cycle will look something like this. And this will stick a y in the end, which is what we want. And we are supposed to print the length and just the cycle itself. We have to stirify things to do this like print join. And also we have 0 indexed internally, and we want to print out 1 indexed, so that is why we have x plus 1. Cool. 4, 1, 5, 3, 1, not the same solution that they picked, but that's fine. Cool. So, we have a wrong answer. That's interesting. I forgot to print out impossible. So, we exit when we find the cycle, so if we got through everything without finding a cycle, then we should print impossible. Okay, I also see that we have a runtime error. Let's take a look at that, because I think that's something else. Yeah, so this can be a problem with DFS, is that in most languages it's like a stack limit or something. And the point is, if the tree is just one, if the graph is one big long path, then you might do like n recursions, right? If it's like this, except it's 1, 2, 3, 4, 5, 6, 7, 8, 9, right, all the way up to 100,000. That's a lot of recursions, and most languages that like default stack limit is not that high. That's also true in Python. Fortunately, there is a way to increase it. So I'll say that we can have 1,000,000 stack frames. That should be plenty. Set recursion limit. The name. Cool. So let's give that a try. So we fixed our bug of not printing out impossible, and we fixed not having enough stack space, and hopefully that means that we got it, which we did. Great. Okay, so let's just see what we were doing. So we need to increase the stack limit, read in the input into an adjacency list, which is how you usually represent graphs, right? So for every vertex, just what its neighbors are. We're going to make a parent in this, it's called the DFS tree. Or I guess it's a DFS forest, actually, if it's disconnected. Anyway, this is a useful thing produced by DFS, and it's nice to know that it's a tree. Right, so this is just where you came from in DFS. So in our DFS, this is like a precondition is that we set the parent. It's kind of good to keep track of that kind of thing. So you sort of know what assumptions you have to work with, and what assumptions you have to make true also. Okay, so for all the children, if it's not the parent, if we've already seen that child, then we've actually found a cycle, and it's a back edge, and it must be our ancestor, right? That's what we argued earlier. because if it can't go to a different subtree because that subtree would have explored us already, is the point. So if it is an ancestor, then we have a cycle of this form, which is like first you follow this edge, and then you follow the path of ancestors back up to y again. So that's what I'm trying to indicate here. So the cycle starts out yx, and then we just add the ancestors of x, including y, because they asked us to print y on both ends. And then we can print the length in the actual cycle, and then exit because we're done. Okay, so that was the whole case if we actually found a back edge, in which case we're done. Normally, the other case is when you haven't seen that node before, it's totally new, and then we should write down that we are its parent, and we should recursively DFS into this. Right? So the difference between the DFS and the DFS, in the DFS you would add it to a queue here, but in the DFS you just like go straight into it. You don't even finish the rest of X's children. So we DFS over the whole graph, over anything we haven't seen. And the point of this is we're not guaranteed that the graph is connected. If it was connected, we could just DFS 0 and that would hit everything. But it might not be connected, so we should do this to hit everything. And if after all of that DFSing we didn't find it, then it must be impossible. And that's it.